In this lecture, we will turn our attention to the core components that bring a PLC system to life. We'll begin with the central processing unit, often referred to as the brain of the PLC, which executes the control program and makes the decisions that drive the system. From there, we'll look at PLC memory, where programs and process data are stored and retrieved during operation. We'll also examine the different types of programming terminal devices used to create, load, and troubleshoot PLC programs, ranging from simple handheld units to advanced PC-based software. Finally, we will explore human-machine interfaces, HMIs, which serve as the link between operators and the automated system, replacing traditional control panels with graphical, touchscreen displays. Together, these topics provide a deeper understanding of how PLCs think, remember, and communicate, both with people and with machines. The Central Processing Unit, CPU, is built directly into single-unit, fixed PLCs, while modular rack-type PLCs typically use a plug-in processor module. Depending on the manufacturer, the term CPU, controller, and processor are often used interchangeably to describe the same module, which performs essentially the same functions. Processors differ in their processing speed and available memory. A processor module can be divided into two main sections, the CPU section and the memory section. The CPU section executes the user program and makes the decisions required for the PLC to operate and communicate with other modules, while the memory section electronically stores the program and other retrievable digital information. The CPU not only serves as the brain of the PLC, but also provides important tools for diagnostics, communication, and operation. On the front of the unit, several LED indicators give the operator quick diagnostic information, showing whether the processor is running, in error, or if outputs are being forced. Many processors also include a key switch with 3 modes of operation: run, where the PLC executes the program; prog, where execution stops to allow editing; and rem, or remote mode, which allows switching between run and program modes through programming software. The processor also features communication ports, such as serial and USB connections, which are used to connect programming terminals, HMIs, or other devices for uploading, downloading, and monitoring programs. Finally, a battery backup ensures that the PLC retains its program and data during a power outage, allowing the system to resume normal operation once power is restored. Altogether, this makes the processor unit a critical component for both control and reliability in PLC systems. Memory is the element in a PLC that stores information, programs, and process data. The amount of memory required depends on the complexity of the program. A simple system with only a few I/O points needs very little memory, while a large-scale system with thousands of I/O points requires significantly more. For example, smaller PLCs like the Micrologix 1000 may have as little as 1K of memory and handle up to 20 inputs and 14 outputs, while larger systems like the Contrologix controller can have up to 32 megabytes of memory and manage more than 128,000 I/O points. Each piece of information stored in PLC memory has a memory location, which acts like an address that the CPU can access. Data is stored in binary form, using ones and zeros, with each binary digit called a bit. 8 bits together form a byte, and bytes are grouped into words, typically 16-bit or 32-bit, depending on the PLC. The program itself, along with all stored data, is written and read by the processor in this binary format. Sections of memory are dedicated to storing the status of the PLC's inputs, and these are called input status files or input image tables. Every input device, such as a switch, has a corresponding bit in this memory table. When a switch is closed, the memory bit is stored as a 1. When it is open, the bit is a 0. This digital image of the real-world inputs allows the CPU to make decisions and execute the control program without needing to constantly check the physical devices directly. A programming terminal device is needed to enter, modify, and troubleshoot the PLC program. PLC manufacturers use various types of programming devices. Early PLCs often used handheld programming devices, which connect directly to the PLC through a cable. These units are compact and inexpensive, making them a simple option for maintenance staff. However, their limited display capabilities make it difficult to work with large or complex programs, so today they are mostly used for small applications or quick adjustments. Today, the most common way to program a PLC is by using a personal computer with the manufacturer's programming software. The computer connects to the processor, often through a serial or USB port, and allows the programmer to upload, download, and edit programs with ease. This method provides a much larger display, advanced troubleshooting tools, and the ability to save and manage multiple programs, making it the standard approach in modern PLC applications. A human-machine interface, HMI, is a device that allows operators to communicate with a PLC. Instead of relying only on push buttons, selector switches, pilot lights, or thumb wheels, an HMI provides a more flexible and user-friendly way to monitor and control processes. Through an HMI screen, operators can start or stop machines, change settings, and view real-time system data. HMIs simplify operator control panels and make industrial systems easier to manage. HMI panels typically feature screens that connect directly to the PLC, allowing operators to read or write to memory locations in real time. These screens provide a visual interface for monitoring process conditions, alarms, and set points. Additionally, in industrial environments, HMIs must often meet environmental certifications to protect against dust, moisture, heat, and other harsh conditions. This ensures reliability in demanding applications such as manufacturing plants, packaging facilities, or heavy industry. That concludes Chapter 2. In the next chapter, we will shift our focus to number systems and codes, which form the foundation of how PLCs store, process, and interpret data. We'll explore decimal, binary, octal, and hexadecimal systems, as well as important coding schemes like BCD and gray code. This background will prepare us to better understand how PLCs handle logic and communicate information internally.